Today we are going to discuss about the physical properties of amines. In my previous lecture, I told you about the amines, its structure and classification, and its stereochemistry. So when we are talking about the physical properties of this particular amine, generally the lower amines, first of all we should divide it into the aliphatic and the aromatic. So first I will talk you about the aliphatic, then we will talk about aromatic amines. When we are talking about lower members of aliphatic amines, they are generally gaseous in its nature, and when we move further they will become volatile liquids, and still higher members of the aliphatic amines, they are generally solid in their nature. When we talk about the physical state of the aromatic amines, they are generally liquid, and higher member in case of aromatic system, they will become solid, and the solid is basically they are low melting solid. Pure amines are generally colorless, but on exposure to the air, they will become slightly colored in its nature. For example, when we talk about the aniline, aniline is colorless, but when we put it for a long time in a stored vessel, its color will become slightly yellowish in its nature. So for using aniline, if it is stored in the storeroom for a long time, it should be double distilled before its use, right? So it doesn't have any color, it is colorless, but if it is stored for a long time, it can develop some color because of some reaction with the air or air oxidation. When we are talking about its odor, generally the lower members, they have fishy ammonical odor, and it vanishes in higher member, right? So these are the some physical parameters like its state, its color, its odor. When we talk further about the physical parameters, physical properties, we should come to the solubility of the primary amines or the secondary amine or the tertiary amines. When we are particularly concerned about the solubility, generally the lower members of the aliphatic system, aliphatic amine, they are water soluble, and the reason for their water solubility is no doubt is the hydrogen bonding, because they contain hydrogen and there is nitrogen hydrogen bond, and that bond is particularly polar in its nature. So when they are mixed with the water, they undergo the hydrogen bonding, and because of that reason they are particularly soluble in water. If we are particularly concerned about the primary amines, and in case of primary amine, we are only concerned about the lower members. But when we proceed to the higher members, then what will happen to the solubility? The solubility will go on decreasing. And what is the reason behind that? Because the hydrophobic portion, that is the R portion, will go on increasing, and that will interfere with the hydrogen bonding, that will interfere with the solubility of that particular amine into the water. So the lower primary amines, they are particularly soluble in water, but when we talk about the larger member, it the solubility will go on decreasing as we increase the hydrophobic portion in case of amines. Now you can see in the slide that when we talk about the boiling point, but before discussing the boiling point, if we discuss about the solubility of the aromatic amines into the water, then our answer will be it is not soluble in water. The reason being there is a big aromatic ring attached with the NH2 group, and that make it hydrophobic, and because of that reason it is particularly insoluble in case of water, right? When we talk about the boiling point and we compare the boiling point of the amines with the alcohol and with the hydrocarbon of the comparable molecular mass, we can came to know about a fact that for example, this is your ethane, this is your alkane, and this is a case of primary amine. And when we look at the molecular weight of these two different compounds, we found that they have comparable molecular mass, and when we compare its boiling point, we have a fact that amines are generally having higher boiling point as comparison to the alkanes. It can be clearly seen into this slide that amines are having more boiling point as comparison to the hydrocarbon of the comparable molecular mass, and reason for its high boiling point as comparison to the alkane is because of its polarity and because of hydrogen bonding, because it will undergo the hydrogen bonding, and because of the hydrogen bonding it will have high boiling point as comparison to simple alkanes. This is another list where you can compare the boiling point of the primary amine with this particularly alkane and alcohol. You can see it clearly that alcohol still having high boiling point as comparison to amines, and amines are having high boiling point as comparison to hydrocarbon. And the reason of this particular comparison, if we compare the boiling point of the amine with the alcohol, is that this is also polar, but the electronegativity difference between this particular nitrogen and hydrogen or carbon and this particular oxygen, this is, oxygen is more electronegative as comparison to nitrogen. So because of that reason it will undergo more intermolecular hydrogen bonding, and because of that reason it will have higher boiling point as comparison to the amines, right? When we compare the boiling point of the isomeric amines, means primary, secondary and tertiary amines, we can find that as you can see in the table that this is the tertiary amine and this is having lowest boiling point. Then when we go to the secondary amine, the boiling point is slightly higher as comparison to tertiary amine, and when we go to the primary amine, the boiling point is highest among these two. So the reason behind that is, as we know that there is no hydrogen in case of tertiary amine, so it will not undergo the hydrogen bonding. It will not undergo the case of hydrogen bonding, and when it is not undergo the hydrogen bonding, at that time we can say that the boiling point is less. When we compare it, that this is having hydrogen bonding, but dipole is slightly less in case of secondary amine as comparison to primary amine. So primary amine is more polar, it will have more dipole, and because of that reason it will have a high degree of hydrogen bonding, and because of that reason the boiling point of the primary amine is more as comparison to secondary amine as comparison to tertiary amine. So if we compare the boiling point data of amine with hydrocarbon and with alcohol, at that time we came to know about the fact that amines are having more boiling point as comparison to hydrocarbon, and amines are having lesser boiling point as comparison to alcohol. When we compare the isomeric amines, at that time we can find that primary amine will have more boiling point as comparison to secondary, and secondary amine will have more boiling point as comparison to tertiary. Here is a list of complete physical properties of amines, in which we are having its formula, we are having its melting point, its boiling point, its water solubility, and about its basic strength. So you can have a look on this particular physical parameter of the amines. Now when we talk about the basicity of the amines, we know that in case of amines, nitrogen contain lone pair of electrons, right? And this lone pair of electron is responsible for basic nature of amines. And we know that amines are basic because of the presence of this lone pair of electron which is present on the nitrogen. Generally, the amines are weak bases and its aqueous solution of amines are generally basic. This is the equation that this is the methylamine, and when this methylamine reacts with water, it will form methyl ammonium hydroxide. It will form this kind of the compound in which it is particularly forming the ammonium ion. It is forming the ammonium ion, and because of this reason this will become basic in its nature because it is now having free OH negative ion which account for its basicity. When we talk about the basicity of the amines, we should be talking about its pKb value, and pKb value basically tell us about the basic nature of amines, or we can also compare the pKa value of the conjugate acid which is formed. For example, this is the conjugate acid of this particular amine, so we can compare the pKa value, and we know that lower the pKa value, the higher will be the acidity of particular acid. So when we compare that, this is your methyl ammonium hydroxide, and when it react with the water, as you know that it will lose the H positive and it will become S3O positive. So when we compare the pKa value, it will come to be 10.64, right? So we can compare it. For example, this is your methylamine, and when this methylamine react with acetic acid, it will form this, that is CS3 NS3 positive, means it will accept the H positive and it particularly acid will lose the H positive. When we compare the pKa value, its pKa value come to be 4.76 and its pKa value come out to be 10.64. so we know that this is particularly a stronger acid as comparison to this one, and this is a weaker acid. So we can find out the pKa value, or we can find out the pKb value. So for the pKb value, if lower the value of pKb, the higher will be the basicity of particular amine. Here is a list in which we can see the pKb value of different kind of the amines and the ammonia. For example, first of all, the basicity of the ammonia and its pKb value is 4.74, then methylamine 3.36, then ethylamine 3.19, then cyclohexylamine 3.34. If we talk about the secondary amines, and in secondary amine we are particularly talking about dimethylamine, its pKb value comes out to be 3.27, diethylamine 3.02, and when we talk about the tertiary amines, its value comes out to be 4.19 and 3.25, the pKb value, which tells us about the basic nature of different type of the amines, whether it is aromatic, whether it is aliphatic, or whether it is heterocyclic. So if we are concerned about the basic character of the aliphatic amine, we can have two effects. One is the inductive effect, and the second effect that will interfere with the basic character of the aliphatic amines is the solvation effect. So when we are talking about the inductive effect, means the number of R groups which are attached with the nitrogen. We know that R groups are electron donating in its nature. So when more R groups are attached to the nitrogen, what they will do, they will release the electron and they will increase the electron density on the nitrogen. So when they increase the electron density on the nitrogen, at that time they will increase the basicity of that particular amine. So when we are particularly talking only about the inductive effect, at that time we may have this order of the basicity, that is tertiary amine will have more basicity as comparison to secondary, as comparison to primary, as comparison to ammonia. But what will happen if we are talking about the solvation effect, means we are talking about the basicity in case of protonated amine, in case of aqueous solution, at that time we know that at that time the basicity will be having this kind of order, means ammonia will be more basic as comparison to primary, as comparison to secondary, as comparison to tertiary. And the reason for this is the solvation, and that will depend upon the hydrogen which are attached with the nitrogen. And if the nitrogen containing hydrogen, if the number of hydrogens are more, at that time there will be more solvation, means there will be more hydrogen bonding with the water molecule. At that time we can say that when NH3 will converted into ammonium ion, it will become NH4 positive, and it is having 4 hydrogen that can undergo hydrogen bonding. Similarly, when we are talking about primary, it will have only 2 hydrogens, and when it will be converted into ammonium ion, it will have 3 hydrogen and they will have hydrogen bonding. Similarly, when we are talking about this particular tertiary amine, it will have only 1 hydrogen because it will get converted into R3 NH positive, so it will have only 1 hydrogen. So we are talking about the solvation effect. At that time the order will become reverse as comparison to the inductive effect. But the actual practice for amines is that these two effects will operate in a combined manner, and when these two effects operate in combined manner, at that time the actual order of basicity of amines will become secondary will have more basic character as comparison to primary, and primary will have more basic character as comparison to tertiary, which have more basic character as comparison to simple ammonia. The reason for this is that in case of secondary amine, both effects are operating, right? That is plus I effect and solvation effect. Both favors its strong basic character. When we talk about the primary amine, that this is more basic as comparison to tertiary, we find out that in case of primary, the solvation effect will overcome the inductive effect. So here the solvation effect is particularly operating as comparison to the inductive effect of the tertiary amine, and then finally come to the ammonia. So this is the actual order of basicity in case of the amines contain only CH3 groups, right? This is containing only CH3 group. If it is having a different group than CH3, then the basic character will be somewhat different. This is the another slide that will tell you that if we are particularly concerned about the basic character of the amine in the gaseous phase, it should be like this. And when we talking about the aqueous solution, in case of methyl, it should be like this. It is because of the combined effect that will operate, and because of the combined effect it will have this kind of basicity order. In the previous slide you can see that when we are talking about the ethylamine, for example, this is your primary ethylamine and it is having pKb value of 3.19, and this is your diethyl amine, that is secondary amine. This is having the pKb value of 3.02. so at that time you can see that this is the particular secondary amine will have more basic character as comparison to tertiary, and tertiary will have more basic character as comparison to primary if we are particularly talking about the ethylamine, right? And this is because of the steric hindrance of the group which is attached to this particular position. So this is all about the basicity of the aliphatic amine. When we are talking about the basicity of the aromatic amines, at that time we can have a fact that aromatic amines are less basic as comparison to aliphatic amines, and the reason for its less basicity is because of the delocalization of this particular lone pair of electron which is present on the nitrogen to the benzene ring. Because of the delocalization of this particular electron, this lone pair is no longer will be available for bonding, right? So this is the reason that's why aromatic amines are less basic as comparison to aliphatic amine. The second reason that makes the aromatic amines less basic is you can see that this nitrogen is attached with this carbon of the aromatic system, and this carbon is sp2 hybridized. When we talk about the aliphatic system, the nitrogen was attached with the carbon that was sp3 hybridized, and when we compare the electronegativity of the sp2 hybridized carbon and sp3 hybridized carbon, we know that sp2 hybridized carbon is more electronegative as comparison to sp3 hybridized carbon. So because of that reason, this particular electron pair, that is free electron pair on the nitrogen, will be tightly held and it will not be available for bond formation with the H positive. So that's why we can say that aromatic amines are generally less basic as comparison to aliphatic amines. Secondly, third, if I am particularly talking about the third point, that when we talk about the stability, so this is the aniline, and when this aniline will be protonated, it will become converted into anilinium ion. So when we talk about the resonance stabilization of the aniline and the anilinium ion, we know that aniline is more resonance stabilized as comparison to anilinium ion. That's why this is the another fact that makes aromatic amines less basic in its nature. When we talk about the substituents which are attached to the benzene ring, at that time we can say that the groups which are electron releasing, those groups will tend to increase the basicity of the aromatic amines, and in contrast to this, the groups which are electron withdrawing in its nature, they will decrease the basicity of the aromatic amines. For example, if we are having NH2 group, if we are having OR group, if we are having hydroxyl group, if we are having R group attached at the para position with respect to the nitrogen, they will increase the basicity of the aromatic amines. But if we are having NO2 group, CN group, CHO group, carboxylic acid group, sulfonic acid group, which are attached at the para position, they will decrease the basicity of the aromatic amines because they will tend to withdraw the electron from the system, right? For example, at your screen you can see that here are two examples, and when we compare the examples, you are having 3 nitroaniline and you are having 4 nitroaniline, and you can compare the basicity that 3 nitroaniline is stronger base as comparison to 4 nitroaniline. The reason behind that is because this particular nitro group is attached to the meta position with respect to this NH2. So you know that NO2 group has two effects, and these two effects are minus R effect and minus I effect, and at meta position only minus I effect will operate, but when it is attached to the para position, both effects are operating, that is minus R as well as minus I. And secondly, there will be more resonance stabilization in that case. So it will make this particular species more stable as comparison to this one. So it will become stronger base as comparison to this 4-nitro aniline. Here is a list in this system that you can compare the basicity of para substituted aniline, right? And these are the different type of the substituents which are attached at para position with respect to this particular nitrogen. So the Y group is this: NO2, CN, bromine, chlorine, hydrogen, CS3, OCS3 and NH2. You can see that if NO2 groups are attached to this particular position, it will be the weakest base at that time, because all are deactivating groups. When CN is attached, it will have slightly more basic character as comparison to this. This will have slightly more basic character as comparison to this one, and this will have more basic character as comparison to bromine. When we are having different type of groups which are activating, that is CS3, OR and NH2, at that time you can have, when NH2 group is attached at the para position, it will have the strongest activating effect and it will have pulsar effect, and because of that reason it will increase the basicity of the aromatic amines. Now the important point about this aromatic amines is that a ortho effect is also observed in case of aromatic system, and ortho effect is basically a combined effect that will have a combined effect of steric and electronic properties, and because of that reason this type of anilines, means ortho substituted anilines, are less basic than simple aniline, and it is irrespective to the electron withdrawing or electron donating power of any group, right? Means whatever the groups, that is electron withdrawing or electron donating group, if any kind of group is attached ortho to the NH2, at that time it will decrease the basic character of the aromatic amines as comparison to alanine, and this is called as the ortho effect. And this ortho effect is only observed because of the combined effect of the steric as well as the electronic repulsions, right? So this is the important point about the aromatic system. Here is again a series on which you can see the basic character of the different type of the substituted anilines, right? When we compare the basicity of the heterocyclic system, that is heterocyclic aliphatic and heterocyclic aromatic, at that time we can say that heterocyclic aromatic amines are weaker base than heterocyclic aliphatic amines. So this is your heterocyclic aliphatic amine, and when we compare its basicity, at that time we can have that this is stronger base as comparison to this one, and this is stronger base as comparison to this one, and this is the weakest base. Reason for this one, we can see that this is the lone pair of electron on the nitrogen, and this is easily available, right? So it will have more basic character as comparison to this one. And in case of aromatic system, if we are particularly talking about the imidazole, it is having nitrogen, and this nitrogen is having lone pair of electron, and this lone pair of electron is a part of aromatic sextet, and because of that reason this is less basic. When we talk about this one, that is, this is a pyridine, and when we talk about the pyridine, you know that the lone pair of electron on the pyridine is not a part of the aromatic sextet, so it should be more basic as comparison to this one. But the reason is that if we talk about the hybridization of these two nitrogen, we know that this is a aromatic system, and the nitrogen here is sp2 hybridized, and when nitrogen is sp2 hybridized, at that time we can say that this particular lone pair is firmly bonded to this particular nitrogen, is firmly available only to the nitrogen, it is firmly attached with the nitrogen, so it will not be available for bond formation, right? So it will become its less basic as comparison to this piperidine. So this is the pyrrole, and if we compare this imidazole and pyrrole, we can say that here nitrogen is present, and this nitrogen is also having lone pair of electrons, and this nitrogen lone pair is not a part of aromatic success, so it will make this particular imidazole more basic as comparison to pyrrole. When we compare that, for example, this is imidazole. In imidazole, which nitrogen, because two nitrogens are present, which nitrogen will be protonated? So this nitrogen can also be protonated, and this can also be protonated, but this nitrogen will be protonated, and the reason for protonation of this nitrogen, as I have already told you, that this nitrogen, the lone pair of electron on this particular nitrogen, is not a part of the aromatic sextet, so it is easily available, and when it react with this H positive, it will form this cation particularly, so aromaticity is not lost in this particular system, so this is particularly still aromatic system. So this is the nitrogen which will be protonated, right? So when we talk about the heterocyclic system, we can say that the heterocyclic aliphatic amines, they are, when we are talking about the basicity of the aromatic amines, there is another factor. And what is that factor? That factor is steric inhibition of the resonance, that is SIR effect. And when we talk about the SIR effect, first of all, we should know about steric inhibition of the resonance. We know that this nitrogen, the lone pair of electron on this nitrogen, is delocalized over this benzene ring, because the orbitals, the symmetry of the orbitals will allow its delocalization. When the symmetry of this orbital will not allow the delocalization, at that time the resonance will be inhibited, and that inhibition is basically because of the sterically crowded group. Sterically more groups if are attached on this particular system, they will now change the symmetry of the orbital, and because of that reason the electrons are not easily available for the delocalization, and they will inhibit the resonance, and this effect is called as the steric inhibition of the resonance. For example, you can see that this is a substate on which the electrons are present on the nitrogen, and these electrons can easily delocalized over the benzene ring. When we have this substate, at that time we can see that this is a bulky group, this is again a group, and these two groups are attached on the nitrogen, and because of that reason now the structure is not very longer planar, and the orbital symmetry of this particular nitrogen and carbon is no longer same. They will not be having the flat geometry, they are not parallelly aligned, and because of that reason the resonance will be inhibited, and because of the inhibition of the resonance, this lone pair of electron on the nitrogen is easily available, and it will make it more basic as comparison to the previous example. This was the example in which this particular lone pair was easily available for the resonance, was easily available for the delocalization, and because of delocalization its basicity will be decreased. But here this lone pair is not easily available because of the steric inhibition of the resonance, and because of that reason it can be easily available for protonation, and it will make it more basic as comparison to the previous one, right? So this is another factor that contribute towards the aromaticity, that contribute towards the basicity of the aromatic amines. Now we are comparing the basicity of the amines with the amides, and we know that in case of amides the lone pair on this nitrogen is basically delocalized, and because of delocalization amides will become less basic as comparison to amines, right? So amides are less basic as comparison to amines. This is a structure of the guanidine, and a question is there: guanidine contain 3 nitrogen, and which nitrogen will be protonated? So our answer will be this nitrogen. This nitrogen will be protonated and it will give rise to the guanidinium ion, right? And this ion is resonance stabilized, and because of resonance stabilization this particular nitrogen will be protonated, and guanidine is the strongest base among neutral organic compounds. So that's all about the basicity of the amines. Tomorrow we will discuss about the method of preparation of the amines.